Hi, Dr. Cook here. Today we're going to be talking about the generalized point mass model and how to calculate for Coriolis effects. All right, so let's just talk a little bit about how we model our projectile behavior. All right, motion can be affected by a number of different things, right? So we start out with you can be affected by gravity and initial velocity. All right, and when we only use those two things, we call that a vacuum trajectory. Okay, that's all that we've got acting on it. If we use the gravity and initial velocity and also include drag, then we're talking about a point mass. All right, so we're accommodating drag, that we are in an air, we're not in a vacuum anymore, but we're just dealing with it as a point mass. Okay. Now, if it's a simple point mass model, that means that we have no Coriolis effects and no wind. And if it's a generalized point mass, then we're including the effects of Coriolis and wind into our model. All right, we can also look at a model with gravity and initial velocity, the drag, and then including the dynamic interactions of our body with the medium. How does the body move around? And we call that body kinematics. All right, and that is what we call a 6 degree of freedom model. Okay, because we have 3 degrees of freedom for location, right? But then we also get another 3 degrees of freedom for the orientation of the actual projectile body. All right, so our generalized point mass model, all right, now this is when we start accounting for wind and the rotation of the Earth into our model. So we can lay that out this way, all right, that our mass times our change in velocity, which is acceleration, is equal to, all right, now this first term is the aerodynamic forces, all right, all of that stuff going on with the air interaction. And then we have a Coriolis force also in here to account for the Earth's rotation. All right. So the Coriolis force isn't quite a force. It has to do with how we get our reference frames, right? So it is a force acting on it because the ground is moving underneath us. All right. So as the Earth rotates underneath the free-flying projectile, from the perspective of us in a firing position and the projectile, it'll appear like there's this force pushing our projectile around. Right? So how do we get this Coriolis acceleration? All right, that has to do with it. We use this lambda vector here. That's our Coriolis acceleration. And we have an equation 9.173 to account for that in different ways. Now, in this, we've got our vector for the Coriolis acceleration itself. All right, that's what we're kind of looking for. And then we can define this omega vector, all right, based on our angles of launch and our azimuth, our latitude that we launch from and what azimuth. Where on the planet are we that is spinning underneath us? And when it's not the vectorized form, that omega is the angular velocity of the Earth. All right, how fast is the Earth spinning? Now, if we use a different value, we could be on a different, roughly spherical body. Okay, if we were on another planet, we would have a different constant to plug in here based on its rotation. All right, but here on Earth, the value is given here on the screen. All right. Our L is the latitude that we are at. Okay, how far north or south of the equator are we? Now, if we look at the globe, all right, if we are in the northern hemisphere, we're going to define those latitudes as positive, and in the southern hemisphere, we'll define them as negative. All right, it has to do with which way the Earth is rotating, so we got to account for that properly. And then AZ is the azimuth of fire, and we will consider north to be 0 degrees. All right. So we can then look at, through those sines and cosines, what's the effect of firing due north, due south, due east, or due west. All right. Okay. From those, we then get this velocity vector. All right. Where the components in each of the x, y, and z directions, or in this kind of notation, I, j, and k, are our unit vectors in those directions. All right, so starting from that, how might we, more practically calculate this Coriolis acceleration vector? All right, so it's got three components, one in each direction. All right, and they're all multiplied by 2 times that angular rotational speed. Okay, in the x direction, all right, we have to account for both the y and z components. All right. In the y direction here, the j direction, we've got vx and vz factoring in there, accounting for our latitude and azimuth. And in the kth direction, in the z direction, we've got vx and vy factoring in there. Okay, so equation 9.177 would be how we can calculate out those 3 components of our vector. Okay, please note there is a correction in the textbook here, all right, on that y direction component of 9.177 should be a sine of the azimuth, not the cosine. So make that correction in your text. All right, so returning back to our generalized model here, all right, we have a force mass times acceleration equal to the sum of our aerodynamic forces plus a force from gravity plus this Coriolis force that is apparent because of the rotation of the Earth. All right, now if we add to that an assumption that we're in a vacuum, all right, all of our aero forces are going to go away, right? Because we're not interacting with that anymore. All right, and then we can divide by the mass, and we're left with this acceleration on our body being equal to just the gravity and the Coriolis force, right? So this is a way to isolate what is going on just with the Coriolis effects, because we're going to ignore the air. So there's no drag, there's no wind, there's no magnus, there's none of those other things that are going to affect our flight. Just gravity pulling our projectile back down towards the ground and the motion of the Earth underneath it. So if we start with that assumption in a vacuum, and we want to say, okay, how do I calculate these accelerations in the 3 component directions, right? So we can substitute in for that lambda there, right? So in the x direction, all right, our change in velocity with respect to time in x, all right, is equal to, this is equation 9.179, all right? If we do this in the y direction, all right, we get 9.180. And I would like to point out that there is a correction here. Please note, the textbook starts out with a negative sign in front of that v sub x, and it should be positive. So please go back and correct your textbooks. That 9.180 has a positive sign there, all right? And then in the z direction, we get 9.181, all right, shown here on the screen. Now, as you look over these equations, take note that our gravitational acceleration, that negative g, only appears in the second equation for the y direction, right? Remember that this is a coordinate system where y is up, all right, and z is to the side, okay? So y is our up direction, so we've only got gravity acting on us in one dimension, all right? Okay, so what I've got up here at 9.37 is kind of our original equations of motion here, all right, where we're just looking at our location based on gravity. So if we want to include our Coriolis effects into there, okay, so looking at what's going on in the y direction for our altitude, all right, we end up with this term added to the end to give us our Coriolis effects due to the motion there. That's equation 9.214. Now from that, we can define this f sub c variable, all right, just as that new part that we added in, and we're going to call that a Coriolis factor. All right, so if you're reading something about, or you're given a value for a Coriolis factor, that's f sub c, and that's an entire part of the term there on the motion, all right, defined in 9.215. Now, really, that's more of an annotation thing because it just lets us take the first equation on top here and rewrite it with an f sub c to save some space and give us equation 9.216. All right, now as we look at this, we can note a couple things, all right? The latitudes, all right, latitudes only go from 0 to 90. So that cosine of L is always going to be some value between 0 and 1. Okay, for anything that we could possibly be at for a latitude, cosine L has to be between 0 and 1. Now, our azimuths, it's interesting then to look at the effects there. So if we're firing directly due north or due south, think to yourself for a moment, what does that mean? All right. Well, if we're firing directly due north or due south, then that sine term is going to go to 0, and this entire Coriolis portion is going to drop out. All right. So it's not going to have any impact on the elevation of the altitude of where our round is at distance. However, if we were to be shooting due east with an azimuth of 90 degrees, all right, then essentially this Coriolis term here is weakening the gravity term. All right, so how much our bullet drops because the is going to be changed. All right, and that means that our bullet is going to hit high on the target. All right, because when it gets to range, it's going to be a little bit higher than it would have if the Earth had not been rotating underneath it. Likewise, if we shoot due west, all right, you can substitute that azimuth into the sine term there to see that you're going to end up striking low. All right, because of the rotation of the Earth and essentially the target moving relative to where we shot it from. All right. All right, so that concludes this video, getting into some of the math and the equations that we use to account for these effects. See you in class.